This video is about the tangent function. This is AP Precalculus topic 3.8. If you appreciate this content, please give it a like. In previous videos, we learned that the tangent of an angle theta is equal to the sine of theta divided by the cosine of theta. Also, if the terminal side passes through the point x, y on the circle, then the tangent is equal to y divided by x. This leads to the fact that tangent is the slope of the terminal side, because y is the rise and x is the run, and slope is rise over run. So we can think of tangent theta in these three ways, and I want you to hold all three of these ways in your head at the same time. Tangent is sine over cosine, tangent is y over x, and tangent is the slope of the terminal side. Let's use our understanding that tangent is the slope of the terminal side to develop the graph of the tangent function. Let's examine what happens to the slope of the terminal side as our angle theta increases from 0 to pi over 2. When angle theta is equal to 0, the slope is also 0 because this is a horizontal line. As the angle theta increases, the slope also increases. As our angle theta approaches pi over 2, the slope gets steeper and steeper, more and more positive. When theta is equal to pi over 2, the terminal ray is now vertical, and we know that the slope of a vertical line is undefined. Specifically, the slope is undefined because the value of the slope is infinite. In other words, the limit as theta approaches pi over 2 from the left of tangent of the slope is equal to positive infinity. Now let's investigate what happens between pi over 2 and pi. We notice that as the terminal side passes pi over 2 and moves into the second quadrant, the slope becomes very steep but negative. In fact, as theta approaches pi over 2 from the left, the slope is approaching negative infinity. In other words, the value of the tangent function is approaching negative infinity. From pi over 2 to pi, the slope transitions from negative infinity down to 0. As theta passes pi and enters the third quadrant, the slopes go from being negative to being positive. And the slopes transition from being equal to 0 to getting more and more steep as we approach 3 pi over 2. The slope is approaching positive infinity. Notice that every time the terminal side is vertical, the slopes are undefined because the slopes are approaching positive infinity or negative infinity. Therefore, you will see vertical asymptotes in the graph of the tangent function at pi over 2 and 3 pi over 2. In fact, you will see another vertical asymptote every half turn around the unit circle. Here's the graph of the tangent function. Notice the asymptotes at pi over 2 and 3 pi over 2. We will hit those same vertical slopes if we rotate clockwise to negative pi over 2 and negative 3 pi over 2. Here's the general form of a tangent function with the transformations a, b, c, and d. As always, the a value represents a vertical dilation compared to the parent function y equals tangent theta. The c value is still the opposite of the phase shift, and the d value is still the vertical translation compared to the parent function. But what about this period? Recall that for any sine or cosine function, the period was always given by 2 pi divided by b. But that was because the period of each parent function was 2 pi. So the period of a transformed function was the original period divided by the b value. However, you can think of the period of a tangent function as the horizontal distance between one asymptote and the next asymptote. For example, the distance between pi over 2 and 3 pi over 2 is pi radians. So that's the period of the parent function. So it makes sense that the period of a transformed tangent function will be the period of the parent function divided by b, just like it is for sine and cosine. So we just need to keep straight this difference. For sine and cosine, we always found the period by taking 2 pi divided by b. For tangent, we will take pi divided by b. Example 1. A portion of the function f is shown above. The graph of f can be written as f of x is equal to a times the tangent of bx plus d, where a, b, and d are constants. Find the values of a, b, and d. Notice that the c value is missing. That means that c is equal to 0, and there is no phase shift. Since there is no phase shift, that means one period of the tangent function will start right at 0. Sometimes we think of the period of tangent as running from asymptote to asymptote, but you can also think of one period of the tangent function as going from x-intercept to x-intercept, or in general it will be the midline intercept to the next midline intercept. So I'm going to think of it that way. So the beginning of this period starts at the first x-intercept at 0, and then ends at the next intercept at pi over 2. Since the period starts at 0 and ends at pi over 2, that means that the period is pi over 2. We just learned that the period of a tangent function is equal to pi over b, but this can be rewritten as b is equal to pi divided by the period. So I'm going to use this to find the value of b right now. So the b value is going to equal pi divided by the period, which is pi over 2. When you divide by a fraction, you multiply by the reciprocal. So the b value will equal pi times 2 over pi. The pi's cancel out, and we are left with a b value of 2. The d value corresponds to the midline, and we can tell that the midline is still y equals 0, because this is where the tangent function changes concavity. See how it goes from concave down to concave up right at the x-axis? That tells us that the x-axis is still the midline. So d is 0, and we don't need to write anything. But what about the a value? The a value is the vertical dilation compared to the parent function. So let's examine some output values on the parent function. At the quarter period, the output value is 1. Let's compare that to the output value of f at the quarter period. First of all, where is the quarter period? Well, remember that a full period goes from asymptote to asymptote. So from the middle to one asymptote will be half the period. So the quarter period will be right here halfway between the intercept and the asymptote. So at this quarter period, we see an output value of 1. Just like the parent function. So there is no vertical dilation, so the a value must be 1. And we really don't have to write that. So we just found that a is 1, b is 2, c is 0, and d is 0. Example 2. The function h is defined by h of x is equal to 4 times the tangent of 2x plus 5. What is the period of h? We know that for a tangent function, the period is given by pi over b. So in this case, the period will equal pi over 2. And that's it. Example 3. Let g be the function defined by g of x equals 2 times the tangent of x over 3 minus 1. Which of the following gives the vertical asymptotes to the graph of g? I'm putting this statement in a thought bubble because you don't need to write this down. But in your mind, you should be thinking, okay, tangent is sine over cosine. The asymptotes will be where tangent is undefined. That's where the denominator is equal to 0. So here's the part that you need to write down. The cosine of x over 3 is equal to 0. When the denominator equals 0, that's when we have an asymptote. So we just need to solve this equation for all values of x. Next, you solve for x over 3, the stuff on the inside, by asking yourself the cosine of what is equal to 0. On the unit circle, cosine is the x value. So where will the x values equal 0? X values will equal 0 here and here. And it will keep equaling 0 at these two places as we go around and around the unit circle multiple times forever. But the first time through, we will call this pi over 2. So we have one solution at pi over 2. Now, if we were just listing out solutions, our next value, where cosine will equal 0, will be here at 3 pi over 2. However, I'm not going to start making a list because we do not have a limited domain. We are looking for the infinitely many solutions to this equation. So instead of listing the next value, let's ask ourselves how many radians is it from the first solution to the next solution. Hopefully you can see that it's a semicircle that's happening from one solution to the next. So that is an increase of pi radians. Now if I kept going, I would get another solution when I come back to the top. That's going to be another pi radians. So every time I go pi radians, I get another solution and another solution and another solution. So I can get the infinitely many solutions by adding multiples of pi. So I'm going to put pi k where k is any integer. This gives me the multiples of pi that form the infinitely many solutions. Finally, I can get x by itself by multiplying both sides of the equation by 3. Multiplying on the left by 3 gives me x. Multiplying pi over 2 by 3 gives me 3 pi over 2. And multiplying pi k by 3 gives me 3 pi k. This is an expression for the infinitely many asymptotes, and the answer is C. Example 4. A portion of the function k is shown above. Which of the following could be an expression for k? I'm noticing that 2 of the answers have a d value of -2, while the other 2 have a d value of +2. Given those two options, it's easy to see that the curves change concavity at -2, so we can eliminate options B and D. Options A and C have different B values. Option A has a B value of 1/2, while option C has a B value of 2. So let's calculate the B value and see which one is a match. First, we need the period. From midline intercept to the next midline intercept, the input values go from 0 to 2 pi. So that's the period. We know that the B value will be pi divided by the period. So in this case, B will equal pi divided by 2 pi. The pi's cancel out, leaving a B value of 1/2. And this corresponds to option A. For example 5, we are going to practice evaluating the tangent function at special angles. But first, a quick side lesson. I want you to memorize the sine, cosine, and tangent of pi over 4, pi over 6, and pi over 3. Let's run through them right now. The sine of pi over 4 is 1 over radical 2, or if you rationalize this, you get radical 2 over 2. The cosine is the exact same thing, so we have 1 over radical 2, or radical 2 over 2. The sine of pi over 6 is 1/2, and the cosine of pi over 6 is radical 3 over 2. When we get to the sine and cosine of pi over 3, we simply reverse these. So the cosine of pi over 3 is 1/2, and the sine of pi over 3 is radical 3 over 2. Tangent is sine divided by cosine. So, since sine and cosine are the same thing at pi over 4, the tangent of pi over 4 is 1. That's anything divided by itself is going to give you 1. When you get to the tangent of pi over 6, we are doing 1/2 divided by radical 3 over 2. The denominators will cancel each other out, and you are just left with numerator over numerator. So that is 1 over radical 3. If you rationalize the denominator, this is equal to radical 3 over 3. Again, when you divide sine by cosine, the denominators will cancel each other out. That leaves you with numerator divided by numerator. Radical 3 divided by 1 is radical 3. So that's the tangent of pi over 3. Obviously, for this exercise, we are working with the tangent function. So focus on the fact that the tangent of pi over 4 is 1, the tangent of pi over 6 is 1 over radical 3, or radical 3 over 3, and the tangent of pi over 3 is radical 3. Part A, the tangent of pi over 6. Well, we just saw that the tangent of pi over 6 was 1 over radical 3, also known as radical 3 over 3. Part B, we just saw that the tangent of pi over 4 is 1, and we also saw that the tangent of pi over 3 was radical 3. Part D, what about the tangent of 5 pi over 6? First of all, in what quadrant is this? Well, I'm going to think of pi, which is right here, as 6 pi over 6. That helps me understand that 5 pi over 6 is pi over 6 less than this, placing it into the second quadrant. The angle between the terminal side and the x-axis is called the reference angle, and in this case the reference angle is pi over 6. This is important because the tangent of 5 pi over 6 will be the same as the tangent of the reference angle pi over 6, except it might be positive or it might be negative. Since we know that the tangent of pi over 6 is 1 over radical 3, or I could have said radical 3 over 3, the tangent of 5 pi over 6 will either be 1 over radical 3 or negative 1 over radical 3. So in quadrant 2, we can see that the slope is negative. See how it's going downhill? And tangent is the same thing as the slope of the terminal side. So since the slope is negative, tangent will be negative in the second quadrant. So the answer is negative 1 over radical 3, or you could say negative radical 3 over 3. Part E, in what quadrant is 4 pi over 3? Well, let's think of pi as 3 pi over 3. Then 4 pi over 3 will be pi over 3 more than 3 pi over 3. That places it into the third quadrant. Again, the angle between the x-axis and the terminal side is called the reference angle. Since 4 pi over 3 is pi over 3 more than 3 pi over 3, the reference angle is pi over 3. That means the tangent of 4 pi over 3 will be equivalent to the tangent of pi over 3, except it might be positive or it might be negative. The tangent of pi over 3 is radical 3. So the answer will either be radical 3 or negative radical 3. In quadrant 3, the slope is positive. Therefore, the tangent is positive. Part F. In what quadrant is 7 pi over 4? We can think of pi as 4 pi over 4. If we double this, then what we normally think of as 2 pi, we can think of as 8 pi over 4. This helps us realize that 7 pi over 4 is pi over 4 less than 8 pi over 4. That places it in the fourth quadrant. The reference angle is pi over 4, right here between the terminal side and the x-axis. So the tangent of 7 pi over 4 will be the same as the tangent of pi over 4, which is 1, except it might be negative. And in fact, in the fourth quadrant, we see that the slope is negative. Therefore, the tangent of 7 pi over 4 is negative 1. The terminal side of 3 pi over 2 lands right on the y-axis. Because the terminal side is vertical, the slope is undefined. Therefore, the tangent of 3 pi over 2 is undefined. The terminal side of pi lands on the x-axis. Since the terminal side is horizontal, the slope is 0, so the tangent of pi is 0. The terminal side of pi over 2 once again lands right on the y-axis. Since this terminal side is vertical, the slope is undefined. So the tangent of pi over 2 is undefined. Hey guys, don't forget to like and subscribe, but also if you found this video helpful, there's a lot more where that came from. You can click the upper link, which will take you to the whole unit playlist, or you can click the lower link, which will take you to the next video in the playlist. See you there.